This video is about the last basic gas law, which is Avogadro's law. And basically what we want is to look at Avogadro's law from the context of experiments that we can see in simulations, and also from the context of the kinetic molecular theory of gases. So in order to understand Avogadro's law, we have to review about it. It says that if you increase the number of particles inside a container of gas, inside the number of particles of a gas in a container, the volume actually also increases. And if you remove or you decrease the number of particles in the gas, the volume decreases. And obviously, because we are looking at N and V, we have to keep the other variables constant. So we have to keep pressure and temperature constant. So in order for us to kind of look at an experimental simulation of this one, we have to go to this animation here. So I have here an animation. So take note, the pressure right now is 97.2 and the temperature is 300 Kelvin. So let us kind of jot that down. So the pressure is around 97.2 atm and the temperature is around 300 Kelvin. And please take note that we have to keep these constant. And if we take a look at the particles, right now I have 416 particles. And again, please take note that in reality, we don't count particles as individual. We count them in moles, but in this animation, because we cannot deal with moles, it's in the quintillions and septillion and sextillion in number, so we have to deal with a smaller number of particles. But in this case, you have 416 number of particles. Again, that can be seen here, the number of particles, 416. And what we do is, remember in Avogadro's law, we have to keep the pressure and temperature constant. So you have to keep that pressure to be at 97.2 atm, and then we have to keep the temperature at 300 Kelvin, and then we change the number of particles. Okay, we change the number of particles, and we look at the volume. Again, the volume here is not that clear, but let's just assume, because there's no measurement here, but let's just assume that that's one meter cube, 1 cubic meter, just so that it's easy to calculate, right? And then let's just take a look at if it increases into half, or if it increases into twice the size, if it decreases into half its size, and so on. So what we essentially, the idea here is we have to keep the pressure the same, we have to keep the temperature the same, and we only change the number of particles. For 416, let's increase this. Okay, the only thing is, here in my animation, I can keep the pressure constant, but I cannot keep the temperature constant at the same time. I have to choose. Either I have to keep this temperature constant, or I have to keep the pressure constant. So it's unfortunate that I cannot do that, but there is still a way to do that. Just remember that our temperature is 300 Kelvin, our pressure is 97.2 atmospheres, and then our number of particles is 416 particles, and then our volume, again, let's assume that this volume here is 1 meter cube. Okay, so observe the volume, and let's pump in more particles. So from 416, let's increase this. So let's increase this to 1,000 particles. See? Now at first you might say, sir, what, the volume did not change. You increased the number of particles. You increased the number of particles, but the volume did not change. Well, that's because I was not able to keep the temperature constant. You see here, the temperature is 100 Kelvin. If you remember, our original temperature was 300 Kelvin. Now the pressure is still the same, 97.2. So it's 97.2 after, but the volume, the temperature, it was 300 Kelvin. Now it becomes 125. So let me reiterate that 300 Kelvin. It should be 300 Kelvin. It should remain the same. So to do that, to do this, I have to manually increase the temperature. Okay, I have to manually increase the temperature. So from 125K, I have to increase it to 300. So let's observe. Let's stop at 300 Kelvin. 300 Kelvin, turn it to 50, 280, 295, and 300. Good enough, 300. So notice that now the pressure is 97.2, the temperature is 300 Kelvin, so close enough to 300 Kelvin. So pressure is 97.2, Kelvin is 300, and then the number of particles is now 1000. See, so now from 416 it's now 1000. You changed it, and now we can observe what happens to the volume. So remember, the volume was kind of like this a while back, but now it's increased. It's increased like one and around half, right? So because it was somewhere like here, so more than half, right? So it probably increased to something like 2 point something meter cube, right? So this is a proof, class, that the Avogadro's law worked. You see, if you increase the number of particles, you pump in more particles, the volume decreases. You see, from 416, remember the pressure is the same, temperature is the same. From 416, we made it 1000 particles. Now, from the volume, which is 1 meter cube, it now increased into 2. Obviously, this is an estimate, but you can see from here that it was originally somewhere here. Now it's this big, so it's more than twice its original size. So that's the idea behind why we can think of why we know that the Avogadro's law is valid, because we can make experiments and really quantify the number of particles. If we increase the number of particles, it should increase the volume. If we decrease the number of particles, we should decrease the volume. It's kind of like blowing air into a balloon, right? If you blow more air into the balloon expands more volume. If you release some of the air from the balloon, you let some of the particles escape, the balloon shrinks and the volume shrinks down into smaller value. Okay, so that's the idea behind the experimental proof from the simulation. Now let's take a look at how can we think about this from the perspective of the kinetic molecular theory. So again, the idea here is, again, similar to the idea of pressure inside the container and pressure outside the container. So originally, let's say you have 416 particles inside. So those 416 particles, those 416 particles kind of hits the wall and produces a certain pressure. And let's say the pressure is, again, for simplicity's sake, the pressure is 1 atm. And so therefore the pressure inside is 1 atm. Pressure outside is 1 atm also. So this door or this collapsible wall doesn't shrink. It also doesn't expand because the pressure inside and the pressure outside is the same. And again, your N here is 416. Let's say your temperature is, again, 300 Kelvin, right? Now, and then your volume is, let's just have this as 5 liters. That's 5 liters. Now, again, what happens is if you add more particles, so for example, from 416, you add more particles, 1000 particles. What happens is, because there are more particles inside, there are more particles that are hitting on the wall. If there are more particles hitting on the wall, more force on the wall over the same area of the wall. So that gives you more pressure. So what actually happens if you increase this 416 to 1000, the first thing that's going to happen is that the pressure will increase let's say it increases to 2 atm. Again, these are just values, or let's make it exact. So if we increase this to 832, 832, which is double, then the pressure also, 832 from 416, you increase it to 832. The pressure also doubles because there are now twice as much particles hitting on the walls, more force, and therefore increased pressure. And again, the idea is if the pressure inside now increases, which now has 2 atm, right? So now this wall will move forward because the pressure inside is stronger than the pressure outside. So this gets pushed, and you increase, and then the volume increases, right? So this volume increases to 10 liters. It becomes double also. And then what happens is, because the volume increased, remember when the volume increased, that means the walls are now further apart. So even if there are more particles inside, the area is now bigger. So if the area is bigger, even if there are more particles inside, even if there's bigger force, technically speaking, on the wall, because the area is also bigger, the pressure drops down, returns to the normal, which is 1 atm. Okay? And if the pressure inside is 1 atm, 1 atm inside, 1 atm outside, so that wall will stay the same, and the volume will not anymore expand. So you see, again, what you really do is you increase the number of particles, and because of that, the pressure increases. And because the pressure increases, it pushes the wall to expand. But as the wall expands, that means the walls are further apart, meaning the particles can now hit the walls less frequently, which drops the pressure back into its original, which is 1 atm. And again, while the wall is being pushed apart, obviously the volume increased because the wall expanded. And then from there, again, because of the expansion of the walls, the pressure inside also drops, returns to normal. So again, even if technically speaking the pressure here changed temporarily, the effect is it's as if it never changed, because it started with 1 atm and it ended up with 1 atm. So that's why we say P and T is constant. But again, if you have to be strict about it, if you have to kind of make a narrative in your head, what really happens is it temporarily rises, causing the volume to expand. And then when the volume expands, it went back to its original one. But all in all, from start to finish, the end result is the same. The starting point is the same as the end result. So it's as if the pressure did not change. Okay? So that's how you think about the Avogadro's law from the perspective of the kinetic molecular theory of gases.